Okay, so let's kind of recap where we've been and where we're going. So we said way back in Module 1 that statistics is a process for making decisions from data. So we said that statistics is a rational process which you could replace with science if you wished for making decisions from data. And so we started our first step towards demonstrating this goal by introducing categorical variables. So in Module 2, we started talking about categorical variables. And these are variables whose values take on categories, okay? They don't measure the amount of something. And in Module 3, we learned how to do exploratory data analysis. We learned how to take a data set of categorical variables, plot it, and extract the important information. So we learned how to do EDA on cat vars. In other words, we plotted the categories down here, and we plotted the percentages here. So maybe we had something like this. Okay? Now we wanted to go a little bit further. So this decision that we're going to make with a categorical variable usually involves making a generalization about the population parameter from the sample statistic. And so if we think about what we learned in Module 2, one of the things that we learned is that when we were thinking about a categorical variable, we were thinking about some population. We were generally thinking about one category of interest. Okay, so maybe this would be our category of interest. And we were interested in if we had all of the values for this categorical variable, this is a binary categorical variable, what is the one thing we'd want to compute about our category of interest? And that is the percentage of all the people in the population in my category of interest. So we have this parameter pi. Okay? This is a parameter, and this is the percentage of all people in the population in our category of interest. And so this decision that we wanted to make was on the value of pi. We almost never get the population, right? It's too large, everyone's not accessible, et cetera, et cetera. So this decision that we wanted to make involved us taking a small sample of size n, computing a sample percentage, and from the value of the sample percentage, being able to say something about the population percentage. And this is a really hard process. And so we have to know, in order to be able to work on this problem, we have to know what sample percentages from this population look like. And so in Module 5, we introduced in Module 4, we talked about measures of relative standing. And we talked about how to compute percentages from normal distributions, right? So this was really about percentages of values that have a normal distribution. Okay? And then in Module 5, we brought everything together. So Module 5 was about the sampling distribution. In other words, this is what the population of sample percentages look like, right? So we talked about the sampling distribution for P, the sample percentage. And the take home from this was that if our sample was good, and we talked in Module 1 about what a good sample is in general, random and large enough. And in this chapter, we gave specific conditions for what was good enough. What we found out was that these population percentages had a normal distribution. They were centered at the population percentage. This was their mean, and the standard deviation was given by this. Sometimes called the standard error, right? And this was our picture. And this length here corresponded to a standard deviation. And so then we saw in Module 7 how to make decisions, okay? Once we had all this information, we put it together in Module 7, and we talked about hypothesis tests. I'm going to use the abbreviation HT for hypothesis tests. So these were the hypothesis tests for the population proportion. And what we had in mind, and this was a good question. Somebody asked, well, how can you ever get this distribution? Because we've been saying since the beginning we can never get the population parameter, right? So how can I get the population percentage and even get this distribution? Isn't this all useless? And the answer is no. We're going to see later on that if we have a large enough data set, we know the population percentage for all practical purposes. In other words, the practical significance of the difference between the sample estimate we have from this ginormous sample and the actual population percentage is so small it can be neglected. Okay? So we can know it if we have a large enough sample. We can be so close that for all practical purposes we know the population percentage. We don't know it exactly, but we know it close enough. So in hypothesis tests, this is based on the idea that we have a prior belief about the value of the population parameter. And we're testing this. This is the null hypothesis, and we're testing the null hypothesis. And we talked about the three different scenarios that can arise in which we can test the population proportion, right? We can be testing a claim, a change can occur, and we can want to see if it affected the population, or we could be interested in seeing if a population has a certain property. Okay? So we talked about the three scenarios that can arise where we can see this. And finally, we talked about the hypotheses themselves, right? So we talked about how the alternative could be testing a couple of things. The alternative could be testing to see if the value of the parameter was less than our previously believed value. I'm just going to put this in here for emphasis. This is the value of the population parameter under the null hypothesis, what we believe with the null hypothesis. So we could test to see if it's less than. We could test to see if it was not equal to. Or we could test to see if it's greater than. And we went through examples of each of these, right? So this was the helmet, the motorcycle helmet. This was the rat empathy. And this was the Colgate. I'm sorry, this was the rat empathy, and this was the Colgate, where we were testing the manufacturer's claim. So now we have a really good idea from this picture as to how we make decisions from categorical data. And this is worth reviewing and making sure that you understand this. And I want to emphasize again how interconnected everything is. This is how statistics works. We can't learn something in Module 2 and then forget it in Module 7. It doesn't work that way. What we want to do in this module is we want to start doing the same thing, but now for quantitative variables. So I'm going to change a few of these things, and we're going to see that pretty much everything else stays the same. So in Module 2, we also talked about quantitative variables. So these were variables that measured the amount of something. They had units, right? Time, length, weight, area, percentages, right? These are count data. These are all examples of quantitative data. And in Module 4, we talked about the EDA of quantitative variables. And what we saw was that quantitative variables were richer, right? They had much more going on. So when we plotted them, we got a histogram that was approximating some sort of population curve, okay? And here, let me draw this a little bit better. So we had some sort of histogram here maybe that looked like this. And this histogram was estimating, this histogram came from the sample, right? So this is the value of our variable. And this could be either counts or percentages, it doesn't matter. And the idea was that we were trying to figure out what this population curve looked like. And what we saw was that in order to describe this quantitative variable distribution, we needed to provide 5 pieces of information, and the 2 that were most important were the sample mean and the sample standard deviation. And so we've talked about how we think of the sample mean as being the center of these values, where most of these values are kind of centered around, right? And the sample standard deviation as being a measure of the width. And one interesting question occurs, which is, why are we interested in the mean? Notice that for this distribution, the sample mean is not the center of the distribution, because I've drawn this to be right skewed. And so you might ask the question, why don't we use the median? The median is always the safe choice, right? If it's skewed, the median works. If it's symmetric, the mean is equal to the median. So why is it that everyone knows about the mean and we rarely use the median? And the answer is, it's the sensitivity of the mean to changes in these values in their distribution that makes it not so good for describing a data set, but makes it very good when we're doing hypothesis testing. I'm going to come back to that point. So notice that the mean is sensitive to how the values are distributed, right? When we have a skewed data set, that shape, that skew pulls the mean out. When we have outliers, right, the mean's affected by it. And we're going to see that it's this sensitivity that makes it not good for exploratory data analysis, but makes it very good for making decisions from data. Okay, we're going to apply the same things in Module 4. We're going to need the fact that they're normal. And then in Module 6, we talked about the sampling distribution. So kind of our goal here, let me go back up here. Now we're having some quantitative data, some quantitative variable. And if we have all the values of that quantitative variable, what is the parameter of interest? Well, it's going to be mu. Right? It's this fancy looking u. And this is going to be the mean of all the population values. This is the population mean. And what we were interested in here, and we wanted to make decisions about the value of this population mean. This is where we're headed. The same way we wanted to make decisions about the population proportion, the parameter for a categorical variable. Now we want to make decisions on this. So when we took our sample, what did we compute? We computed the sample mean, x bar. So just like we wanted to know what the distribution for the estimators were when we had a categorical variable. So just like we wanted to know the distribution for the sample percentages, in the same way, in order to play the same game for a quantitative variable, we want to know what is the distribution for the sample means. This is what we have to know. So in Module 6, now we're looking at, or we were looking at, the sampling distribution for the sample means. And what we saw, the central limit theorem told us that under the appropriate conditions, these sample means were centered at the population mean, and their standard deviation was the standard deviation of the variable. And so sometimes people put a little x here to make really clear that this is the standard deviation of the variable. This is the standard deviation of x bar. And this is the standard deviation of our variable. Two different things. Okay? And now, with all of this, we're going to play the same game and do hypothesis testing, now not for the population percentage, which is the parameter for a categorical variable, but the population mean, which is the parameter for the quantitative. And one of the things I'm trying to impress, notice that I'm just erasing and changing the blanks. I'm trying to impress upon you that the structure and the logic of what we're doing is exactly the same. And also trying to show you how the things that we learned earlier fit in with the things that we're learning now. So it helps you make better sense of what we're doing and where you might have to go back to kind of refresh a little bit. So now we're doing the hypothesis test on the parameter not for a categorical, but for a quantitative variable, which is mu. And we're going to play the same game, okay? We're going to have some prior belief about the population mean, mu, which we're going to call mu sub 0. This is going to be our null hypothesis. And we're going to see the same three scenarios work, and I'm going to talk a little more about that in a second. And we're going to play the same sort of game. Okay, we're going to see that now we're testing to see if the mean and not the population parameter, the population proportion, the mean is less than our previous believed value, not equal to our previously believed value, or greater than our previously believed value. So just to make this all kind of consistent, right? So this kind of explains the logic of what's going on, how everything is hanging together. I want to talk very briefly about the sort of problems we're going to look at. So we've already talked about the three scenarios we could come across when we're testing a population proportion. I'm going to talk very briefly about the type of scenarios that we see when we're looking at a hypothesis test for a population mean. So generally, these sorts of things occur a great deal in industry. And there are situations where we're either looking at financial data or we're doing some sort of quality control. So we're going to look at two particular situations here. So this will be scenario 1. So some sort of change occurs, okay? Basically what we're testing to see is we're testing to see if mu has changed. And these sorts of scenarios are very common. They occur anytime you're looking at financial data. It could be ticket sales, it could be stock prices, and here's kind of the basic sort of situation here that we have. We could be looking at the price of some quantity over time. Okay? It could be a financial instrument like a stock. It could be the amount of sales that Boeing has made daily. It could be the ticket sales at the Orlando airport, whatever, okay? So we have some sort of time series, maybe like this. And we're going to look at some little window here, okay? So we get in this window, and the price seems to kind of oscillate about some value. Okay. So this is the mean mu naught. And now the challenge of businesses is they have to make decisions very quickly in order to stay competitive, right? If they wait too long to make a decision, their competitors will make it ahead of them and gain market share. If they take too short a period of time, they'll have too little data. And we saw what happened. Small data sets, estimators are all over the place. They're not really reliable. So the idea is that now we have some current data that maybe looks like, say, this. And what we want to know is this evidence, and maybe we have a few values, okay? So we want to know, is this data evidence that the overall mean has changed, or is this just part of the random variation in the data? And so people use this a lot. I had a student that used this successfully to detect pump phases in penny stocks. It works incredibly well, okay? So people use this a lot in stock market analysis. We're going to look at a second scenario. So this is generally when we're looking at any sort of financial data. The second scenario is kind of related to testing the manufacturer's claim. And in fact, there's variations that can be morphed into that. And this really deals with quality control. So we talked a lot in Module 3 about standard deviation. Why is standard deviation so important? Well, for a business, it's important because it's a measure of how consistent your product's performance is. We don't want things that are going to have high standard deviation. There's a lot of variability. And that sounds good, but both in financial markets and in manufacturing, it's bad. This is called volatility in financial markets, and this violates quality control. So here's kind of the idea. And we'll look at a few of these. Suppose you're filling up Raisin Bran boxes. Okay. And you advertise that the contents have a weight of 16 ounces. And you have some sort of assembly line, right? And you're picking boxes randomly. And you're computing the weight. So this is maybe box 1. Okay, I take it off the assembly line, dump out the contents, and say this is 16 ounces. and I get a value maybe down here. Okay? And then I take box 2 and weigh it, and maybe it's here. Okay? Box 3 is maybe here. Box 4 is way down here. And I want to know, I'm going to take these 4 weights, okay, we'll call them X1, X2, X3, X4. I'm going to average them. And I want to play the same sort of game now. I want to ask myself, is this evidence that the population mean is no longer 16? Is this evidence that they've been a change? Notice that Raisin Brands neither wants to overfill the box, right? Because then they're losing money, nor underfill, because they're going to leave themselves open to class action lawsuits, right? So we're going to do some sort of testing like this. These are the 2 scenarios that you tend to see at most. And they're all kind of variations. You can work with human data. Are human beings getting taller? Okay, you can look at a lot of different scenarios, but they generally fall into one of these 2 categories. So I hope that introduction kind of gives you a little sense of where things are at. I know when you take statistics, everything is just kind of thrown at you. There's a lot of new symbols and terminology, and it's hard to kind of see the logic, which is really the main thing. One of the things I strongly recommend you do, and I really want you to listen carefully, when you're working on these problems, flow them. Okay, so a really good piece of advice when you're working on these hypothesis test problems is you want to first of all get the context. And you remember how we talked about when you're reading a problem, how to get the context. Parameter, variable, population, right? Then the variable, then the population. Then you want to figure out what it is you're doing, because we're going to do more than hypothesis tests, right? So you want to figure out what is the question asking. Now that you have your bearings and you understand what everything is. And by the way, the other thing you want to do is you want to assign numbers to values. So if you see something like 26.2 and you're told that this is a mean, you should try to figure out, is this a population mean or is this a sample mean? This is really important. Things like sample sizes, okay? So you want to assign numbers to quantities. If you can't do these first 2 steps, you can't reliably do problems in statistics. You have to do these things, myself included. Okay, I've done this longer than most of you have been alive, and I go through the same process. Okay, it's the same thing every time. You have to figure out the context. You have to assign the numbers to quantities. Then if you're doing a hypothesis test, you have to figure out what is the alternative, right? Then you have to determine the hypotheses. And usually you start off finding the alternative first, because why? Well, that's the thing you're trying to prove, right? Okay, I hope that's a good overview and you got a lot out of that. We're going to dive right into hypothesis testing because you guys have been exposed to the logic before in the previous module. You understand what's going on, and now we're just going to jump straight into StatCrunch and working word problems. All right, thank you.